In this video, we'll be looking at how to solve rational inequalities. And we're going to start off with a graphical approach, which will have quite a bit of familiarity. So given f at x equals 2x minus 3 over x plus 1, we're going to determine if f at x is greater than 0. And we're going to do this graphically, so we need to find our intercepts, our asymptotes, and some key points. So to start, our x-intercept is going to be 3 over 2, comma 0, because we're looking at the numerator and setting 2x minus 3 equal to 0. For our y-intercept, we're going to set x equal to 0, and we would get 0, negative 3, because the numerator would be 0 minus 3. The denominator would be 0 plus 1 to get the following. The vertical asymptote comes from the denominator. What would make the denominator equal to 0? That would be x equals negative 1, or setting your denominator equal to 0 and solving for x. And finally, our horizontal asymptote would be 2. Because of the degree of the numerator and denominator is the same, we could look at the leading coefficients. So that is 2 over 1. And now I'll just start roughly plotting these values on my grid just to get a visual before I go to my key points. So there's my vertical asymptote, there's my horizontal asymptote, and I'll just label the lines. We have an x-intercept at 1.5 and a y-intercept at negative 3. In terms of the key points, I would use one value to the left and one value to the right of the vertical asymptote. So to the left would be at negative 2. So if I evaluate f at negative 2, that would be 2 times negative 2 subtract 3, which is negative 7, and then negative 2 plus 1, which is negative 1, to get negative 2, comma 7. Next, a point to the right would be at 0, and we already have that point. If I wanted another, I could maybe use 0.5 just to get another point on there. But that is enough information. And at this point, I could also test for my endpoints. I could test values for x is 100 and x is negative 100 to see the behavior around my asymptote. I'm not going to show that, but I would expect when I plug in 100 to get a value under 2, so let's say 1.99. And if I were to plug in a value like negative 100, I would expect 2.01, something like that. To see the behavior around the vertical asymptote, I'll plug in a value super close to negative 1. So on the right side, maybe I try negative 0.99, and I would see a very large negative number. And if I plugged in negative 1.01, for example, I would expect a very large positive number. So now here is our sketch. And now we want to see when is the function greater than 0. Well, this entire arm will always be greater than 0. And this point from the x-intercept onwards will be greater than 0. So f at x is greater than 0 when x belongs to negative infinity to the asymptote and the x-intercept to infinity. So that's your graphical approach, but we could also do this numerically using a sign analysis chart. Now, when we do polynomial inequalities, we use the x-intercepts to create the intervals. For a rational function, we use the x-intercepts along with any vertical asymptotes, because this vertical asymptote can result in a change from a positive region to a negative region, like we actually observe in this question. So, I am going to put negative infinity. My asymptote was at negative 1, and I'll make a little note that that's an asymptote. And my x-intercept is at 3 over 2, and then there's my infinity. Now I'll pick a test value. I'm going to test -2. I'm going to test 0, and I'm going to test +2. And now I'm just going to go into my function, into the numerator, into the denominator, and see what the signs would be. My numerator is 2x minus 3. 2 times -2 is -4, minus 3 is a negative number, and that's going to be divided by -2 plus 1 is negative. Two negatives make an overall positive value, which is what we see graphically as well when we're to the left of the asymptote. When I test 0, the numerator will be negative, the denominator will be positive. That will give us an overall negative sign. And when I test 2, that would be 4 minus 3, which is positive, and then 2 plus 1, which is positive. And there it is. Now, in terms of us answering the inequality, we want to be greater than 0. That would be here and here. And those are the exact same values we got from the graph. But the sign analysis might actually be a more efficient way, because graphing rationals can be a little tedious, especially if you have more asymptotes to deal with. So let's try another example. We're going to solve the following inequality. But this one, we have a quadratic in the numerator and denominator, which means we need to factor first. So when we factor the numerator, we'll have x plus 2 and x plus 1. The denominator is a difference of squares. So there it is. And now my x-intercepts are -2 and -1 coming from that numerator. My vertical asymptotes are positive and -4. Now for this question, we do have quite a few brackets and factors involved, so there's another way we can organize our work here. And I'm going to put my number line here from -infinity to +infinity. And on the sides, I'm going to write out all of my factors. So I have x plus 2, I have x plus 1, I have x plus 4, x minus 4, and then my final. Okay, and now I'll create my number line. -4, -2, -1, and +4. So now let's see the signs. I'm going to test x plus 2 first. So when I put test -5, that'll be a negative value. If I test -3, that will be a negative. If I test -1.5, that's positive now. If I test 0, that's positive. If I test 5, that's positive. For x plus 1, -5, negative, 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 positive, once I get past -1. Now x plus 4, negative, but the minute I put -3 in, I'm now in the positive regions. Next, for x minus 4 will be negative, negative, still negative, still negative. Once I get to testing a value greater than 4, that's when we finally get that positive value. And now I can look. I have 4 negatives here. That's an even number. They all pair up. That will be overall positive. These two pair up to be positive, but we still have this leftover negative. 2 negatives here make a positive, just a lonely negative, and those are all positive. And now we can look and see here, we want to be greater than or equal to 0. That's greater, that's greater, that's greater. In order to be equal to 0, I also need to include my x-intercepts. Now, a little note, 4 is a vertical asymptote, and so is -4. So in terms of the positive interval, we want to be between -infinity and -4. I don't want to be equal to -4 because that's a vertical asymptote, so no thank you. Another positive interval between -2 and -1, those are zeros. I can be equal to them, and if I'm equal to them, then I'll be equal to 0, which is what the question is asking me for. And finally, we want to be between 4 and infinity. 4 is an asymptote, so I'm not going to put my square bracket there. And that's it. For the final one, negative 3 over x plus 7 is less than negative 4 over x plus 8. We need to make sure that one side is 0 so that we can compare positive versus negative, which means let's bring one of the fractions over. And that negative will turn into addition. And now we're comparing for less than 0. And now I need to unite these fractions with a common denominator so that I can actually look for those asymptotes and intercepts. So the first fraction will get multiplied by x plus 8 and the second by x plus 7. Now if you look at the denominators, they are the same. They each have an x plus 7 and they each have an x plus 8. My numerator, I will do some distribution. So negative 3x minus 24, and then positive 4x plus 28, and all of that's less than 0. Let's collect our like terms in the numerator. And now we are ready to identify intercepts and vertical asymptotes. So for this question, we only have one x-intercept coming from that numerator at negative 4. We have two vertical asymptotes coming from the denominator at negative 7 and negative 8. And again, I can set up my chart with the factors like I did in the previous example, or I can organize my work and just keep track of the positives and negatives within the fraction and look at the overall quantity within one row, like I did in the first one. All right, so we're looking from negative infinity to infinity, and we're looking at negative 8, negative 7, and negative 4. Negative 8 is an asymptote, so is negative 7. Okay, and now time to test. I'm going to test negative 9, negative 7.5, negative 5, and 0. So when I put those test values into x plus 4, so if I just add 4 to each of the test values, that will remain negative, negative, negative. This will be the only positive one. If I put those test values into x plus 7, so just add 7 to them, negative, negative, these now turn positive. For x plus 8, negative, and everything else will be positive. Well, let's look at our overalls. 3 negatives make a negative, 2 negatives make a positive, 1 negative makes a negative, no negatives make a positive. And now let's see what we want. We want to be less than 0. Those are the two intervals, from negative infinity to negative 8 and negative 7 to negative 4. And because we don't want to be equal to 0, we will use our curved brackets only. And there we are. There's our rational inequality using our sign analysis. We still need our factoring skills to get our x-intercepts and our vertical asymptotes, and we use those values to do a sign analysis and compare positive versus negative intervals.